unsupervised learning. So, can some of you tell me what is training data?
Training data is data for supervised learning, data with labels, and we tune our model. Like we learn our parameters by looking at the data and its corresponding labels.
So basically, training data is the data which we give to algorithm to learn, right? To learn the parameter of the algorithm. And testing data is the data from which we can evaluate how good is the model. So in this morning, we talked about linear regression, where you try to fit a line and try to do the prediction. That was the first thing, right? So second was logistic regression, where we wanted to, instead of doing regression, we wanted to do a classification. So now we'll be talking about unsupervised learning. In this case, we don't give label, we only give data to the algorithm. And algorithm has to decide and put that data in a cluster or assign a label to group of data. So in unsupervised learning, let's talk about clustering. So what is clustering? It is the organization of unlabeled data into similar groups of cluster. So, and what is cluster? So cluster is the collection of items which are similar between them, and this is similar to data item in other cluster, right? So if you are in one cluster, you should be similar with that cluster, right? And you want to be dissimilar with other cluster, right? But clustering can be done in many ways. So how it can be done in many ways, and you need to decide how you want to cluster. If you see this, you can cluster like this one in a circle, inside and outside, and you can cluster in this same data in different way. Right into half, left and right half, right? So we need to be careful on the criteria we want to do clustering. That is very important. Now, how did the clustering came? This is the history behind John Snow, who was a London physician. Yeah, Game of Thrones. But this guy, there's something really good, like in Game of Thrones. But here this guy found was, what happened was, there was outbreak of cholera, and there was death. And this guy wanted to find why there is outbreak in cholera in particular region, and why people are dying. So what he did was, he found the solution, like where there was a well, there's a big map. Basically, he found some of the well where the water was polluted, and where the people were dying. Basically, found a cluster of people dying in some close location to the well. So like that, he found what was the problem. So he looked around and he found that the water was polluted. So here, then they were able to treat the water and the problem was solved. So basically, you find the cluster, with the help of clustering, he also found the solution. Thus, exposing both the problem and solution for this. So this clustering can be done in many ways. In this case, he could not have known label, right? He didn't know the label here. But the cluster helped him define the label, find the problem. So how you do a clustering? First thing is, we need to choose a similarity measure. Like I showed you before, circle. right? In a circle, we can choose either inside or outside, right? There was ring. Or we can do up, right, and left half.
Inside or outside.
So in that case, how do you do that? So if a cluster is similar, the similarity measure will be large. If something is similar, the similarity will be large, right? And
Measure will be large.
in the dissimilarity measure, you want to be distance of the cluster, you want to make it very far. So similarity should be very large, and the distance between the clusters should be very far. So this is one way of doing defining a similarity measure when you are doing a cluster. If you see here, good clustering and bad clustering. So you can there you see that there are three clusters where the distance between the cluster is far, right? Within cluster is low, and among the cluster it is large. And here, this is the example of bad clustering.
Among the cluster it is large. And here, this is the example of that.
Okay, this is how you sometimes you have to be very careful. What are you going to optimize? What are similarity metrics you are going to choose when you do k-mean clustering? So, for example, when you have a data, let's say we have a data points d in Rn, where xi is a vector which belongs to Rn and n is the number of dimensions. So in that case, you want to make the data in Rn, you want to choose a cluster. So there, what you need to define a cluster. Okay, how many clusters you want to group this data, right? Data point. That when you are doing k-mean clustering, you need to know that. Second thing, what you need is a centroid to start, to initialize how you are going to do that. And third thing is a stopping criteria. So here we use sum of square error. So similarity matrix. So when you do a clustering, these three things are very important. One is the number of clusters you are going to assign, a centroid, which is your initialization, and third is the similarity matrix. So you can judge how good is your cluster. So let's say we don't know that here we clearly do not know the clusters, right? But we say, okay, we want to assign a cluster to this data. So we choose three centroid. Okay, we say, okay, here we give the centroid randomly. But we don't know also what to choose. One cluster, one centroid, two centroid, or is there two clusters, three clusters? This is also something we need to do. For sake of example, we'll keep it simple here. Okay? So let's just choose three centroid. So in first iteration, you calculate the distance between the clusters. So here, C1, we calculate the distance between the cluster and we assign that centroid to those particular cluster. Okay? So here you see, these are the points which are close to this centroid. So we assign the point, these all those points to C1. Likewise, here we assign. Third, here also we assign. Once we assign, the second thing what we do is calculate a new centroid, right? Because now you have another group of cluster, you need to find a centroid. First was you randomly choose them. Second step, you need to find the centroid based on the first you have chosen cluster. Okay? Here, another thing is what we did. Now we want to update our centroid. So we updated it, and we'll have a new centroid. So based on this, we say this is the first iteration. We found a centroid and we found the point near to the first centroid. So in second iteration, what we do, we again calculate the distance between the centroid and the point along with the centroid to see whether it is close to the centroid or not. If it is close to the centroid C1, then that will be one cluster. If it is C2, that will be another cluster, and C3, then it will be another cluster. So here, at N, when our centroid, if it's not changing, then we know that we converged. We cannot change anymore. We cannot. The centroid will not change in this case. So we know it is finally done. So we assign that based on the cluster. So before moving, I will give you some of the assignment right now, so that it will be more clear, like what exactly is the centroid and what exactly is the similarity criteria we are using here. Without the example, it's very difficult to understand, but I'll give you one coursework where you can see how it is working basically.
We need one for each group.
So one row make one group or what?
Yeah, one row.
So basically, we're assigning each row to a group.
So we'll be
Work
assigning
together.
each row a group so that you can work together. There is an algorithm for clustering. You discuss with your partner in each row. So, in the question, there is medicine A, medicine B, C, and D. And the attributes are X, 1, 2, 3, 4, 1, 2, 4, 5, and attributes another is 1, 1, 3, 4. So, we are doing clustering, that means we do not have a labeled data. We only have attributes, right?
We are doing clustering.
There's two attributes, X and Y.
You only have attributes, right? X and Y.
Not going to
Can you understand that? Just hit them and you can go around this and that. If you want to see, you can see it. Just don't show it to them.
Regarding this clustering, I want to give you some practical example, right? Example. So for example, here we have to have people, right? So we don't know where are you coming from, let's say. I didn't ask you where did you come from, right? So but I have some information that you took a bus, or you took a plane, or you took a train, and maybe how long you took to reach here, right? So these are the attributes, information I have. Then I want to basically cluster you, maybe. I want to assign you some clusters, so that based on this attribute. And then if I assign you one of the clusters, then ultimately what will happen is that in a cluster, there will be people come from same region, you know. So this is the clustering. I mean, we do not have a label example, but we have other information. Then minimizing the distance. I mean, the clusters, there will be some centroids. Centroid will be something, a location. Okay? If someone is coming from Pokhara, he took the bus. If someone is coming from Bangalore or Mumbai, so he took the plane. Right? Or maybe we can have other information, like how much did you pay for your travel? Right? If someone paid a lot of money, and the large amount of money, he is very likely to come from very far from the Kathmandu.
If someone paid
So the clustering is used in such problem.
it's very likely to come from.
So this is the practical example. I can see some of the people from Ansel. So the example will be, so you have customers, right? So then you'll have different variables. So how much a person actually spends money in a call. You also have some kind of information that they subscribe some kind of, you will have some kind of subscription, right? I mean, 3 calls after 10. And if someone speaks, talks in a phone every night after 10 p.m., he is more likely to have his girlfriend or boyfriend. You know? So based on these attributes, you can cluster them and then you can identify. Right? Another example will be if someone is using his phone during the office time and from a single location, then he is more likely to be someone who is working in the office. Right? So we can use these attributes and cluster and try to find, the people belonging to a group. So this is the idea about this clustering. Thank you.
So this is the idea about this clustering. Thank you.
So here is the algorithm for clustering. First you choose how many clusters you want to assign. So we gave you 2 centroids. So that means we basically want to cluster them in 2 groups, right? So first thing, when we do clustering, what we choose? A matrix, right? Since this is 2D, we can choose distance matrix. Okay? You know the formula for distance matrix? Under it, x2 minus x1 1 square plus y2 minus y1 whole square. So what you need to do first? So first, we need to find the distance between two centroid and each of the points. Try to find the centroid, the distance. Let's call it a matrix T, D0. So, do we have any volunteer who want to calculate the distance? Distance metric. Do we have anyone?
First we will take C1 at this point and C2 at this point and calculate distances of C1 of all the points with respect to C1. With C1 and the first point coincides, so their distance will be 0. Then there's a unit distance between C1 and the second point. With the third point, the distance will be 3.61. You can calculate the Euclidean distance. So x1 will be the centroid, and x coordinate of centroid, and y1 will be the y coordinate of the centroid, and x2 and y2 will take the x and y coordinates of the points. So, if you put for the first, x1 is equals to 1, 1, and y2, x2, y2 will be the points of the points given. So you'll get the distance matrix.
Thank you. So everybody understood this? Does everybody understand this? No? Okay. So, first we assign a centroid in a cluster, right? So, here we said we will assign this point as a centroid, C1, and another C2, right? And this centroid, here, this point is 1, 1, C1, right? And C2 equals 2, 1. Another centroid, right? We said we will pick two centroid. So now we have 4 points, which is medicine A, medicine B, C, D. So let's calculate for the medicine A. So medicine A is x is 1 and y is 1. It is here, right? Medicine A. So when you have to calculate the distance between medicine A and C1, what do? You basically put the value here, right? So x2 minus x1. So you can put 1 minus 1 whole square plus 1 minus 1 whole square. And the solution will be 0. Because both the cluster and the point are in the same place, right? So the distance will be 0. Likewise, you take the medicine A and calculate the distance between another centroid. So here, when you plug in here in the equation, the distance will be 1. Likewise, when you do the math, you will end up with this distance for each medicine A, B, C, D, based on the cluster 1 and 2. Okay, the upper one is C1, the distance between the medicine and C1, and lower one is the C2. Now, let's go to another question. Once we have a distance, now what do we want to do? We want to assign the points to a cluster. So here, these are the points in a cluster 1. Distance between cluster 1 and cluster 2. Distance between the centroid and the points. So based on this, the criteria was minimum distance, right? If distance between the centroid and the point is minimum, then we assign that point belongs to that cluster, right?
To calculate the distance matrix, we should calculate the Euclidean distance between all the 8 points and the first centroid and the second centroid. So this is the distance of the first point with the first centroid, and this is the distance of the second point with the first centroid, and so on. And these are the distances of the 4 points with the second centroid.
Okay, thank you. So basically we did what we did before in the first iteration. Now it's like repeating that again and again. So if you see here, we'll have a new cluster. So based on this distance metric, we write a new cluster here, which will give Z1. So here is the new cluster. Does everybody understand this new cluster? Did you understand how we got here? So this was our initial cluster, and this is our second cluster, right? So in another iteration, again, we assign point to a cluster, a new cluster. So again, the new thing we need to calculate is new centroid, right, based on the new cluster. Can somebody calculate a new centroid for me? Any volunteer? New centroid? Did anyone already calculate the new centroid? Basically, you repeat the thing what you did before. Just repeat it. So tell me, what happened to the centroid? Did it remain the same like before in the previous iteration, or did it change? It changed, right? Why did it change?
P2 came to.
So why did the centroid change? Anyone? Yeah.
Because we are calculating the centroid from a new group.
Exactly. So we have a new group, so the centroid will change. Thank you. So our new centroid will be this one, 11 by 3 and 8 by 3. Did everyone get this one? Maybe in points or something, but are we all in the same page? Okay, just let me know if you didn't understand, basically. So, again, what will be the next step? Same thing, right? You compute a new distance from point to the centroid, right? We are in second iteration, so our centroid change. So basically the new centroid is 1 by 2 and 1. In our first iteration, the centroid didn't change because we had only 1 point in that cluster, and in our second iteration, we had a 3 point in the cluster. Right? In the first iteration, first centroid didn't change, second centroid changed. In the second iteration, both the centroid changed, right? So this is our updated centroid in the second iteration. So can someone calculate the distance between new centroid and our point? Anyone? Can anyone calculate the distance? We are getting there. We are about to finish. Can you calculate the distance between the centroid? So this is new centroid, and you need to calculate this. Okay, right. So based on this, and write a new cluster, what we get based on this. I give a name G, so it will be a G. So here, if you see in your graph, does it make sense? Does it make sense that medicine A and medicine B, medicine A and medicine B should be in one cluster, and medicine C and D should be in another cluster, right? Does it make sense? Why it makes sense? Why it makes sense? It's very intuitive. Like, why it makes sense? Yes. Basically, they are close to each other, right? Distance metric. Within cluster, their distance is low, and among cluster, their distance is high, right? So that is why it makes sense. So now if you go and redo it, basically your centroid will not change. That's how we know your algorithm converged. If you do the same step again, calculate the new centroid, basically now the centroid will not change. It will remain like what we had previously. So now we'll look something different, because we did a mathematics. Now, does everyone have a laptop? I need your laptop. Just take it out. I told you before, but just take it out, and one row, one should do. And go to this link here. So here you will see the clustering. There is a simulation. Now here you can really see how it works. Now we know the mathematics, we understand how it is working. Now we will know how it works. So, you should get to this page. Okay? Now we'll do a clustering, same thing, but in this simulation, now you can understand here. So, you might have so what I recommend everyone is to have 3 cluster, random point, 3 cluster, and 3 centroid. So if you have a 3 cluster, it makes sense to have a 3 centroid, right? So let's do this. You might have a different distribution of data, but you should get the same thing. I'll give you few minutes to connect to the internet and go to this website. Now we already know. Here we already know what we want to do, right? You can imagine, right? Here is 3 cluster. So number of centroid you want to choose is 3, right? So in first iteration, what will you do? You calculate the distance between this centroid and the point. So what we do in first iteration, here if you go here, find the closest centroid. Okay? So we click here. You got the centroid. Yeah, you got the cluster based on the centroid, right? In the first iteration. Does it make sense? Does it make sense here? Anyone? Sorry? Does that make sense? This point is near. So this is the first iteration, right? This is the first iteration. It still has not changed. We are in the first iteration. Now what we need to do? We need to update the centroid, what we did in second iteration. Like that, we calculate a new centroid. So like that, we have another. Right? So we do it. Now, we keep on doing it until our centroid doesn't change. So now here we have a bad clustering example because it doesn't always converge. Why it doesn't always converge? Because in this case we didn't. Okay, in this case the centroid was not properly initialized. Okay, that is why initialization parameter. When you start a parameter, so centroid alpha parameter, right? Random parameter you choose. So you need to be careful when you do clustering how to choose a parameter. So let's do again. Let's do this with a new centroid, same thing. So what do you think? Will this converge? So let's do first iteration. Based on the first iteration, the points are okay. Third, right? So here again we did convert. So this is some of the thing in clustering. Many of the algorithm, if you do not initialize your initialization parameter initialization, if it is not good, then you might never convert. So this, okay, tell me here. Now tell me, will it convert? It should, right? Okay? Right? Second iteration. Third. So we keep on doing the iteration until it converts. So here also it didn't converge. Yeah, maybe this one might converge with it. Yeah. Yeah, this will, now, we'll do the thing is we need to do a lot of initialization now. Then after it will converge at some point. That is one of the disadvantages as well. So here, it will converge, the algorithm will converge and will have a thing called clustering. So what I want you guys to do, assign the number of clusters to 5 and number of centroid, let's do 5 for now. And try to simulate it, I will see. Try to simulate it and try to converge it. Okay, try to make it in a cluster. Whereas in K means you needed to decide how many centroid you need to choose to do a clustering, right? So here if you see, let's see, we choose 5 nearest neighbor. If you choose a 5 nearest neighbor, tell me this point, where will it belong? And if you take, so tell me where will it belong this point in this first ring, which is 5 nearest neighbor, and within that ring. Green, right? We agree on that. So how did you get to the solution? You looked at the neighbor in some distance space here, and then after you assign the new point, to the number of neighbors around them. Okay? It is based on voting scheme. So if we take the whole space, tell me where will this belong? This is one of the very, if you can understand Kevin, then this is like really easy to understand. So first tell me how many neighbors we consider if we decide to take the whole space here.
10.
How many points are there? Count the green points and count the red points.
30.
How many?
26. Total points are
Yeah, total points, except the.
except the 26.
And how many green points and how many
13.
red points?
13.
Okay, in that case, what will be the solution? So there is ambiguities, right? So we got a problem in K-mean. I wanted to show you. There is a, like in K-mean we have a problem. In nearest neighbor also we have a problem. If we have this kind of ambiguity in the neighbors, okay? So let's go to something different. So we'll start support vector machine. So let's say we want to classify this circle and this cross, okay? Or 0 and the cross. So we can use a line to classify, right? You can put a line there. There is a good classification. We are doing 100% classification. Accuracy is 100, right? There are. Can you give me one algorithm which can classify linearly? Any algorithm you can classify like this. Exactly. This morning, right? But this is also a good classification, right? This is as well. We can fit line in many ways here and get 100% classification. But let's say it looks good when the line is in middle. Okay, it feels good. When the line is in middle, what will be in middle? So let's see example where we have the same points but we have a noise. When I doing this, there is a noise in observation. Okay, in your data points. So in that case, same thing we can do. And we can fit a lot of line. But the thing is, we can do 100% classification from those lines, but when there is a lot of noise in the data, then it would be really difficult, right? Which line to use and how to classify. So in that case, coming back to no noise case, the line which is in middle seems to be good and we want to do that. So this is exactly what support vector machine does. Basically, it tries to flatten the margin between two class and do the classification. Okay? So we can flatten the margin, but we can flatten like this as well. The margin, right? We can do like this as well, right? But the good thing is the maximum margin. So support vector machine algorithm is an algorithm which will classify the data with maximum margin. This is the difference between support vector machine and other algorithms like logistic regression. So it is also called maximum margin classifier. That means it will classify the class having a big, large, flat margin, to be said. And another is you only need few examples, because here in this case, these are called support vector. So these are the points which are supporting this line, which are fat narrow. Okay. So here, in this case, we do not need all the points. Imagine you have millions of data. The storage cost will be high, right? So if you can come up with some good example, good points, and these are the good points to keep because it is holding the hyperplane, and we know this that beyond this, all the examples would be classified without 100% accuracy. So another advantage of supervector machine. So now we saw there are a lot of cases. Sometimes you can classify your data because it is deterministic, right? There is something. But sometimes it is non-deterministic. Basically, what does that mean is your data is nothing but noise. You are trying to model the noise, okay? You cannot model the noise, right? So the function is non-deterministic. And another is partial observability. You cannot observe the whole underlying distribution of the data. So in that case, it will be difficult for you to build a good model. One is you cannot because it's noise. Another is there's a lot of information you cannot get. Another thing is bounded resources and also algorithm bias and representation bias. For example, in a representation bias, we don't know whether the data is linearly separable or not. And another is algorithm bias is if you try to classify, if you try to use a linear classifier for non-linear, then you can never do it, right? No matter how many parameters you tune or what initialization you use, you cannot. So here, let's see the cases of the how data can be distributed. Okay. If you see here, we can separate this data right here with a single line here. So in this case, we know data can be separable. Next case, you see here, we can clearly see we can separate the data, but in this case, can we separate this red point and blue point using a linear classifier? What do you think? Right? So here, you need to understand how the data is there. But in that case, we need to do transformation of your data. Okay? So here, we transform the data. Now we can see, we can separate. The glass is pretty good. So, before, when we were using a tool example, I showed you that data were linearly separable because it was x and 0, and we can just fit a line and we can do it. But here, we cannot, because the data is not linearly separable. In that case, what you need to do, you need to transform your feature to another space. So in that case, support vector machine is the algorithm which you can use to do linear as well non-linear classification. Okay? So let's see how, what do you mean by feature transformation and that's for the intuition, okay? think the internet is slow. So in that case, in support vector machine, the idea is to transform your features into a hyperdimension space and try to classify them linearly. Okay. Basically, you transform your feature from here 2D to 3D, and in 3D you can. Okay, in 3D what you fit. In 2D we know, like before, there's a line which is classifying. So in 3D, how do you classify? What? Plane. 4D? Hyperplane, right? Or after that it's hyperplane. Everything is hyperplane. So here you can see, like, so how do you know that? So this thing. So another question is, how do you know when using a linear SVM linear with a linear kernel? Okay, I'll come up with the kernel trick. So we use a kernel trick to transform this feature from 2D to 3D. Okay, but before doing that, how do you know the data is not separable? What would be the intuition to do non-linear? Sorry? Yes, it's 2D, but when you have a hyper, like 10 dimension, 20 dimension, 1000, how do you know that we learned this morning? How do you know? It's very easy. So, to know, you need to know how good you are classifying, right? So, classification accuracy. If you see your classification accuracy is just 60 or 50 or random. Below that is random, 50 is a random, most not. So you know maybe this data is not linearly separable. So in that case, you need to choose different kind of kernel. Maybe the data is non-linear. I cannot show you the simulation I wanted to show you, but I don't have it here right now. You can see later. So there, in this case, we use kernel trick. Here we use different kind of kernel. Basically, what this kernel is doing is mapping your data from one space to another space. Okay. For example, okay. So these are the normal kernel used in support vector machine. So first, when you are fitting a line and doing, it was a linear kernel. When you see linear kernel, and if you are not getting a good classification result, you imagine, okay, maybe it's not a problem. It's a problem of maybe a data as well. Maybe we cannot separate linearly. So what you do the feature transformation. Use polynomial kernel to do feature transformation. But what I personally like is a radial basis kernel, because this kernel will project your data into infinite space. Okay. Now, okay, I have here the video. I will show you what I mean by. Just quickly, I'll go through feature transformation, the previous slide which we saw. So we have a data here in 2D, right? And we know we cannot separate it. What you do? You transform from 2D to 3D, right? So what support vector machine does is, now you try to separate. Now you can see you can separate the data there in that space. Well, so basically now in here you Same, the property is same. You try to classify with a flat margin. The margin property will still be there. Okay? And even the slide is there. You can go home and see how it is doing. So it equals this, for example. Okay. Let's continue. So basically, in so-called vector machine, kernel trait is basically a function that you use to transform your feature from one space to another space. So there is a pointable function, radial basis function. You can use that function and transform and see whether your data is classifying. How good is your classification now compared to the linear one? Most of the cases, when your linear is not working, this will work. And you have to, other things are empirical, which kernel to use. Linear, polynomial, or radial basis kernel. You can make your own kernel as well, but there is a criteria. It should satisfy Mercer theorem. Okay, it is a bit advanced stepping. You can make your own kernel as well to do the transformation. So let's see this demo, how support vector machine. Let's see how it works. So if you have a laptop, you can as well try it, get intuition. So first what we'll do, we'll use a linear kernel in some data. You can plot the data with your own way. And see how it works. So, here also you need to be careful that we have a regularizer. Okay, we always have a regularizer in every algorithm which we want to fine tune. And how we do fine tuning, I will discuss later with the help of cross validation. So if you see here, this is a linearly separable case, and if you change the regularizer, so tell me, what is this points called? What are these points? Exactly. Support vectors, because these are the points which are supporting the line there in that case. Okay. And let's try to put some point and try to make it non-linear, okay? So if you see here, it is impossible to classify because now you cannot classify with the line, right? So what do we do? We use kernel trick. In this case, we use RBF kernel. Okay? So when you are using the kernel will have its own parameters to estimate. So if you take the parameter, now we can see you are able to do classification, right? Okay? What I suggest you to do, look in your laptop and try to randomly generate a point and see, because if you get an intuition, then you can really work how it works. So this part of the lecture is all about tuning the parameter and seeing which algorithm to use, how to use. Because this morning we already learned how to code. Now we know how to code in machine learning, right? To use tools and to code. So let's 5 minutes, if you can, anyone can come here and do. Is anyone interested? You can make your own point. Okay, guys, I'll just take a coffee. So try to cooperate. So, okay, I think you guys are interested in going home and doing this by yourself, I guess, or playing with it. So I will let you do that when you go home. I believe you will do it. So we can move, I think. So play with this one and see how it works. You got the idea of colorimetric, linear, non-linear. Now let's go with some of the other things. I think we already did this morning, no? So we already did this regularization this morning because we had to change the format of the lab and lab work so that you don't get tired and you are motivated to work. So we already talked about bias and variance, right? This morning, and a couple of you guys saw in the lab, and you have already had a good, very interesting question this morning. So you already know now how to have a good algorithm, right? But still, when there is training, one training set and one testing set, it is very difficult to have a good parameter. We talked about penalty this morning, loss. So we talked about how to evaluate the algorithm, like true positive, false positive, true negative, false negative, false positive. So do you want me to repeat? I think you already know this because this morning you worked it, so let's go further. Yeah, this one. This one, so imagine you want to model this point, right? Either you can fit a line right here in the first scenario. Somehow we think like it is not a good fit, right? Because the green one is the true model you want to make. And if you start with a line, then what is it doing? Under fitting, right? In that case, you know, you are in a bad fit. How do you know it is under fitting? Because here we can see, okay, this is 2D, right? So how do you know hyperdynamics is under fitting?
Training error is high and testing error is also high.
Exactly. So your training error will be high automatically. If you are not doing good in your training sample, then testing, like, forget about it, right? I will even not test that. So when your training error is high, then you know, like, you are underfitting. And now if you go up, let's say, here you can, if you try to tune your parameter also, you cannot fit good. So in that case, you want to go for another model, right? Maybe you want to fit a curve, okay? So how do you know that your fit is a good here in this case? How do you know you're fit here? How do you know like, oh, I'm doing good in my data? How do you know this?
Error is low on test data.
Yes. What will be the error in the trend data?
It will be nothing, both will be less.
Exactly. Your error will be less in training data as well as testing data. Okay? Or your classification accuracy will be good, high in both training and testing. Now here, it is going through every point, so it is overfitting. How do you know it is your algorithm is overfitting? How do you know this? Exactly. So you will do really good in your training data, but when you give a testing data, you will not do good.
Variance is very high.
Exactly.
The bias is high.
So the morning talk about bias and variance. It's the same concept, same thing. It's the same thing. So can we, if we have a training and testing data, we know that we can fit good, we can underfit or we can overfit, right? But we want to be in the middle, somewhere, based on the data we have. Okay? So this one, I'll not explain. So this is underfitting and overfitting what I taught. So how to handle this kind of underfitting and overfitting? One is regularization. So how to choose the regularization, like the value of the regularization? One thing is you have a training data, like we did in the morning, right? The C value, we increased it, and we saw testing. Okay, we separated our training, our data into training and testing. In training, we put the parameter of the regularization parameter, and we tested it, and we saw it. But is that always good? Is that a good way? Of course, it's one of the good way, but we want to, the data we have, what we expect is, we want to do good in the data we have never seen, right? We have limited data, so you want to maximize the use of this data to do to have a good parameter. Because you have testing, one training. You will be good in this data, only training and testing. But this data can be a lot of things, but you want to be very good for the data is coming, right? Which is coming. So that is the point. And how to maximize, I would say, how to come up with a good parameter from the data you have in your hand. That is the. So in that case, we talk about cross-validation. So here, do you want to do it or I can finish it for that? Do you want to do it or I can finish it? Okay. So in cross-validation, what you do is, in the lab, what we did, we just separated data into training and testing. And we choose the parameter which were doing good enough testing data, right? Training and testing, the accuracy was good. But another technique is a cross-validation. So the famous one is Ribbon outwards validation. In this case, you will test your algorithm with the same set of parameter, which is your lambda in this case. You fix the lambda and you build a model and test with every data you have. For example, if you see here, leave one out. You leave one out and you train the model with a set of lambda c. Let's say in this morning we use 100. I can remember in that one. So you build the model with the rest of the data, taking the 100 as your value 100 as a regularization value, and you test it. First time, you keep the 100 same, you take this data and test on this one. Second time, you take another one, not that one, you keep this one in the model and rest, and you test it. Like that, you test for everyone and you see the accuracy. Like that, what are we doing is, we are exploiting our data, right? We are saying, like, is the 100 good value and leave one out? We are saying this one. We are trying to estimate a good. Now another time, you choose 0.5 instead of 100. You do the same thing. And again, you plot the accuracy of the error. So this is one of the techniques how you can exploit the data. But this is very expensive technique, very expensive. Imagine, okay, you have 100, 200 examples, you can do it. Imagine if you have a millions of examples, okay? Or you have a good example, 1,000, 2,000, it might take a lot of time. Because you have to build a model, test a model, and you have to do a search of the parameter, it takes time. So another one is 5-fold cross validation. So, tell you, it's the same concept. 5-fold cross validation. You have a trainer, you have a data, you want to build a model. First thing was, we separated data. We said, okay, 60 we'll keep for training, 40 we'll keep for testing, what we did in this morning. Leave one out, what was, if we have 500 data, we'll train the model on 499 and testing one. Like that, we turn and do it. In 5-fold cross validation, can someone tell me what we do here? Yeah. So, in 5-fold cross validation, what do you do? Anyone? 5-fold cross validation?
Yes, you take 1/5 of the data for the test and the remaining for the training set.
Yeah.
We have that times, yeah.
So, in 5-fold cross validation, you take the 1/5 of data and do it 5 times. So first time, take this as your test data, build the model. You divide the data into 5-fold, means 5 times, okay? And you test 1/5 every time, okay? Yes. So basically here, this is one technique where you can do it when you decide. 10-fold cross validation. So, can somebody tell me 10-fold cross validation? What do you do in this case? What did you do in 5? What did you did in 5-fold? Anyone? So in 10-fold, you divide your data into 10 different folds, and each time it's the same thing. Each time you train the model and test. For example, here is the first round where you use one parameter and you take one of the fold and test it, and on the other 9th fold you train the model. Like that, you do the second. Like that, you do the third. And each fold here, to be careful, like in 5, you have accuracy, right? You have training accuracy in this case, each fold. Because, so what you do, take the mean of the accuracy, then after, you will know whether the parameter you selected is, or the algorithm you selected is doing good or not. Okay, this is one of the ways. So, tell me what happens in repeated case, repeated 5-fold or 10-fold. You understood the concept of 5-fold, you understood the concept of 10-fold. Now, repeated 5-fold and 10-fold. The answer is just there. So here, if you see here, you are doing in a sequence, right? Here, if you see, you are taking in a sequence, in a fold, but in the repeated case, you will take the data from randomly. It doesn't have to be from this one, okay? It has to be a 10-fold, but inside that fold, the data can come from anywhere from the training set. For example, if you have 100 samples, when you do a 10-fold, in each fold, how many samples you have? 10. Now these 10 samples can come from anywhere, right? Anywhere. You can choose that 10 data, one from here or that. Okay? So the idea is to randomly choose it. Okay? So I think I'm done for today. I'm tired. So very tired. So you guys have any question before? The thing is, I saw some of the people here. Some are doing really good. They know the concept. Some wanted to talk about a feature selection. Some wanted to talk about a lot of things. But seeing the class, we had to change. I mean, we wanted to give an overview of machine learning algorithm and how it works. But if you want, let's say, feature selection, those kind of things, if you are really interested, then we can discuss. For example, I see a couple of people here who really knows how to do machine learning, but they want to improve the skill. I think that was one of the reasons most of the people came here, right? So that can be done separately in a group discussion later, and see how we can improve. But here, the idea was to incorporate everyone. Many of the students, they are good in math here. So the idea was to incorporate and make a lecture rather than talking about the dimensionality reduction or feature selection, complexity of feature selection, those kind of things. Okay?
You'll also use that tomorrow and day after.
Yeah, you will have an advanced. This course was a basic kind of generalization, but the next week, like Vinod will talk, many people will talk. In that case, we give you the basic framework you can understand. You can really, you'll see those courses in advanced courses, how it works.
Yeah, so the first half is mostly, designed to understand the basic. And the second half?
In the second half, we'll talk about state of the art technologies. So no worries. So he recently taught you bias and variance trade-off, right? So it's something like that. We have to make sure that everyone can be accommodated. Thank you.
So I wanted to end this class with this flowchart. Can you all read what's written here? Then I'll read it for you. I got it from MIT Tech Review, and they were writing about machine learning and deep learning and AI. What is AI? And everyone talks about this, right? So we today learned about some basic machine learning algorithms, and then we'll learn more later in the class as well.
Can you?
So you even found it funny. Well, the idea of AI, the reason it's getting popular now is because you have a lot of data and we're looking for patterns. And we saw a lot of examples today when we're talking about supervised learning or clustering and unsupervised learning, SVM. Well, one key component in all of these things is to understand patterns from a lot of data you have. So the way this flowchart starts, it starts asking about what is it you're looking for? Are you looking for patterns? And are you dealing with a lot of data? So if no, then okay, maybe we don't need to do machine learning or all these things we're learning about. But if yes, then great, it's machine learning. Then what it asks the next step you have to ask is, are you being told what to look for? Or is your algorithm being told what to look for? So do you have labels? And if you do, then what is it? Supervised learning, we learned about that today. If it's not, so I will start with just supervised learning. So now it is supervised learning, then you're asking what algorithm to use. If you're using deep neural network, then now you're doing all this deep stuff that is getting a lot of popularity and will use. If not, if you're not doing supervised learning, if you're not being told what to do, then you're trying to reach an objective through trial and error. And we saw that example when we were doing K-means clustering today, right? You choose all this initialization and doing yes and no, and then you have another one you do again. And sometimes you get stuck in a local minima. So you're doing a lot of trial and error. All right, okay. So if you're not doing trial and error, it's saying it is unsupervised learning, and there is reinforcement learning that we didn't really talk about. But the whole idea about this is to motivate deep learning and how popular it is. So in the end, the flowchart is asking, are you using anything that has deep in it? If yes, you're in this amazing world of deep, and if not, you just learned all these boring techniques we talked about today, which is not as interesting in AI as deep learning is. So you have to stay tuned to understand all this deep learning stuff. So I thought it was very interesting to summarize everything we learned today using this flowchart.
So basically, you guys need to be attentive for next week for deep learning.
And you need to know boring stuff to learn exciting stuff as well.
So we'll be uploading this, and there are a lot of slight credit we have to give for the people. So we'll be giving those, you can see the references and everything when we upload.
It's already uploaded in the
Yeah, we'll do a new one as well, okay? From starting from the lab work, okay, we didn't reinvent the wheels, okay? There's no need to do the reinvention of wheels. So we'll give that everything, and
there is lab today.
so now we'll have a lab. Now you will see one of the application of K-means. Like we will basically show you using K-means what can we do. How can we detect objects? So that will be in this class. We'll not ask you to code, but we'll ask you to judge what you did right now. For example, choosing the number of cluster, or those kind of things. With the help of that, we can detect vegetables or detect house from cloud, okay, sky. So it will be interesting, I hope, after this one.
And before we end the class, I actually wanted to do some discussion, thinking about some of the applications where you can use the method you learned today for supervised learning or unsupervised. If you can tell me about the data you have and if you learn new things that you can do using the tools we already discussed for that data. I think that will be a good discussion before we break for dinner. Because I know people here are working on a lot of cool stuff, and they have even started using machine learning. And hopefully today you learned something new that you can use for the data that you're working on. You want to share, anyone? Or we'll have Vinod start with his application and then people can chime in.
Okay. So where do we use unsupervised learning, right? The idea is we don't have any level information, then we try to use this search algorithm so that we can segment or categorize the items, right? So but why we don't use supervised learning algorithm? Because it's really difficult to collect the label data, right? So if you want to detect some collect data, then you need exports. You need to spend a lot of time and the resources, right? So in that case, it's very useful. So it sounds simple, but many of your real world problems that can partially or fully solve with these algorithms.
Can you give us one example?
So one example is that, so here in the class we have male and female. So I don't know, I mean, I didn't see even your picture, but I want to identify whether you are male or female. So but there are some information, simple informations maybe. So maybe I can make a questionnaire or something. It's very easy to call, right? So for example, does he put on lipstick? Does he have long hair? Maybe height? And this kind of pictures, right? So from these examples, so I want to categorize the new one, whether she is male or female. So the first question will be like, so whatever. Huh?
She is.
Oh, she is. It's okay, there's the only difference between S only, right? So, the matter. So now, the first question will be like, how many clusters do you choose? So when you train your model, right? So the first thing you need to know is, okay, how many clusters should I choose? So it's obvious, right? It's 2. Then, I'll simply try to import this information. For example, it's a feature vector, the feature encoding technique. So, it will be something. So we'll have some different attributes. For example, put on lipstick. Okay, if someone put on his lipstick, so it will be 1. If not, it's 0, right? And long hair maybe? So usually long hair, I mean girls, they have long hair, right? So but it's not always true. So if someone has long hair, then how do we put it? It's 1 or 0. Maybe height, right? So but I don't want to be like, I don't want to say that all are shorter, but seeing the statistics, right? But they put on the heels, so they attend the same height. And maybe, yeah, I will keep some kind of threshold here and say that, okay, let's see, is he or she is taller than 5.5 inch or not? It's something like that. And it's like, so it's 5 feet, 5 inch. So if someone is taller than this, then I put 1 or else 0. So this is how we encode it, this information. And then we run this algorithm, and then you have 2 clusters. And when someone new comes in, we'll ask this questionnaire, and then we compute the distance to the centroids, right? And whichever is the distance, I mean this vector, for whichever the cluster is closer, then we'll assign that label for C, male or female, right? So this is a simple example. So there are several cases also. For example, as Taman mentioned, so you can also detect house from the cloud. So the house, the pixel intensity will be something different, and the cloud, the pixel intensity will be something different. So based on the intensity of this pixel, you can basically make, assign it to 2 levels, whether it's a cloud or the building, right? And again, I worked in the demo company before, so I want to take some example from you guys, from Ansel, right? So we used to do some kind of customer segmentation. Some customers, they spend a lot of money, and some customers, they don't spend, right? Someone like, they speak a lot in the night. So we had to design some packs, right? Maybe many of you have subscribed such packs, right? Data packs or call packs. So what kind of data we collect is, maybe when do you make a call, right? In which network you make a call. So usually if you want some kind of packs, then you ask your friend to get SIM the network that you are using. Right? Oh, okay, Ansel has some kind of offer. They are giving some free calls after 10 p.m. Right? Then we take this kind of information, we call this variables or attributes, and we know the numbers, but we cannot use the identity, right? So based on that, we come up with a different kind of clusters of users. Someone who would use in the night, then we come up with search buffer, right? And someone who spends a lot of data, then we send them the data pack buffer. So you can say that, okay, I will identify that, okay, this guy is a data user, he uses a lot of data, then I will send him an offer, okay, there is a data pack, with this money you can buy it. And if I can identify the right person, then he's going to buy that product, So at the end your sale will go up.
So the idea here is to collect features, cluster, and then identify a segment of users, and then you can actually use it for your company.
Yeah, again, like this segmentation is like in what respect you want to segment, right? So if you want to categorize different data users, then the main attributes for you will be some kind of the volume of data they use. All the features won't be relevant. So you have to see some kind of correlation between the data usage, pattern, and these things, right? So every variable will not use as well.
So we'll learn some of those tomorrow.
Yeah, for example, here, in the male and female, if I take some kind of, attributes like, does he have lunch or dinner or not? Everybody has it, right? Everybody eats lunch or dinner, right? Maybe if you ask if someone consume or eat lots of pani puri, then maybe that can be an interesting feature for you to categorize. So the feature selection is also very much important. But if you can come up with some kind of, using your heuristic, using your prior knowledge, if you can come up with some right attributes, then this kind of algorithm definitely works. Right?
Okay, I also want to hear some more examples from people here.
So I guess the most useful thing that I found with today's lecture was the probability likelihood kind of perspective or classification. So generally I used to think it as a discriminative thing, like we need to discriminate between like customer churn prediction. Every company might be doing this, like we want to predict which customers are going to churn. So instead of looking at it as a classification task, if you look at it as I want to find out the likelihood of each customer going to leave this month. So basically, the thing that we discussed yesterday was mapping to it very nicely. The way we said we have some beliefs, and then we have a new updated knowledge, and we change our beliefs based on the beliefs. So I see that happening here. So we have something called gamification in our sales team. Gamification is this concept where we gamify the sales team. So if we use churn prediction and gamification together, the way we discussed before, it is kind of a simulation model. And then you will optimize.
So you use your prior knowledge to say that.
So you know the likelihood of churns, the customers who are going to churn, and you will use that to improve your gamification, optimize the gamification model. So something like
that. That's quite a good point. So we didn't really talk about map estimate in linear regression or stochastic regression or any of these models today, but we only talked about maximum likelihood estimate. But you could also think about it in a Bayesian perspective, like Sir was teaching yesterday. If you have a prior distribution and you want to encode that, then you can start doing it in a map estimate, right? Rather than maximizing the likelihood and getting one estimate, you can have the posterior likelihood, and then you can use likelihood and prior and use the map estimate. And that's another way to think through this part problem. So that's a really good example, yeah.